Hello, good afternoon. I think I have the challenging timing here because, after lunch, it's going to be a real challenge to keep everyone awake here. But I'll try to put a few jokes. I'm not really good at jokes, but let's see how that works. Okay, this one. So I'll be talking about advanced biofuels made from sugars. So I didn't put sugar canes intentionally in because it's sugars. It could be cellulosic sugars, and I think that's something you see in more detail as I go on with my presentation. So my presentation is going to talk a little bit about Amyris. It's going to talk a little bit about the technology that Amyris has developed. I'm also going through a few scale-up challenges since we're now at the industrial scale phase already, and then talk about the biofuels applications that we have in the market right now going. So I'm not sure, I know that a few of you already heard about Amyris and about its history. So Amyris has now, it's going to be 11 years since Amyris out there. It's a spin-off of the University of Berkeley. So I know that many of you are familiar with Jay Kiesling, and actually Amyris was founded by Jay Kiesling and 3 other postdoc students back in 2003. So the start was with a grant from the Bill and Melinda Gates Foundation to develop a process that was capable of produce artemisinin, which is a medication used in the treatment of malaria. So it was basically to find an alternative source of artemisinin, which, as you know, malaria is one of the neglected diseases that we have in the world. So it kills millions of people every year. So there's about 200 million people get infected, that have the disease. They have the disease every year, and they don't have basically the money to pay for the treatment. So Amyris had the challenge to come up with a process that would make artemisinin one of the most effective drugs used in that treatment, to make it available and cheap. And it was very successful. So that's how the company started. So that technology has been transferred now to Sanofi Aventis. So last year we had the production of artemisinin made using this process to cure 70 million people on that. So we're about half of the cases of malaria could be treated using artemisinin coming from these technologies. So it's really an amazing achievement that those guys have made. So Amyris has then, and that was a non-profit project. So part of the agreement with the Bill and Melinda Gates Foundation was that the development of the technology would create a license to Sanofi Aventis, a royalty-free license. So and Sanofi Aventis also produces it on a non-profit basis. So that was part of the agreement. So what Amyris did, Amyris kept the rights of the basic technology. So the patents and were all kept to Amyris for the use in other fields. So one of these fields is the production of biofuels and renewable chemicals. So that's where we are deploying the technology and creating processes and developing materials that are basically hydrocarbons. So Amyris believes it's one of the best in class. So it's one of the most advanced companies in terms of what we call synthetic biology. It's been able to scale up manufacturing not only for the medication artemisinin, but also for farnesene, which is a hydrocarbon that we now produce at industrial scale. And our logo is the no compromise products. So all of the products that Amyris develops they have to be keeping same or better performance than the products that are being replaced, and they have to be coming from renewable sources. So that's the foundation. So we have our headquarters are in Emeryville, California, just across the Bay Bridge. And it's, I mean, if you see the top floors here is where the J-Bay Institute is, and so these floors down here are where Amyris' offices and labs are located at. And this is a picture of our industrial plant, which is in the state of São Paulo, in a city called Brotas, here in Brazil. So basically what the technology is about, we use engineered yeast. So yeast that uses C6 sugars, it can be modified, and we're working on that to use also C5 sugars, so it will be flexible in that sense. So we already have some strains that are able to transform over 90% of the xylose or C5 sugars and metabolize them. Basically what we do to yeast is we change the normal flow of the carbons inside the yeast by doing genetic modifications and creating pathways or expressing pathways that would make the carbons flow in the direction of desired molecules. So as I mentioned, the first one was artemisinic acid, which is a precursor of the artemisinin, the medication itself. So that was the first project. We can see that the same pathway that was used to make the medication can be adapted and adjusted to make another very interesting molecule, which is called farnesene. So farnesene is a hydrocarbon, so it's an olefin with a few double bonds here. So it can be then saturated via hydrogenation to become a diesel or a jet fuel, can be used as a jet fuel, or can also be a precursor to several chemicals, so different chemical applications as well. So this pathway, the isoprenoid pathway or mevalonate pathway, can also be used to produce C10 molecules and C5 molecules as isoprenes. So we're always talking about multiples of the C5, so it's the isoprenoid path. So that's, we can, I mean, using this technology, someone has estimated that we could come up with up to 50,000 different molecules. So, and then the decision is made based on what commercial interest those molecules would have, so in applications that can be used. So there's a lot of applications as well in the field of flavors and fragrances. So we have also agreements with companies like Givaudan, IFF, just to name a few that are interested in that space. So how do we develop this technology actually? Basically, what Amyris has developed is a way to both increase the number of attempts, because when you develop a new organism, new strain of yeast, I mean, there's a lot of trial and error involved in that process. So what Amyris does is create a technology that is capable of increasing the number of attempts, and not only that, but also increasing the quality of the attempt. So we have created processes that will allow us to produce as many as possible strains. So our productivity in terms of strains has to be increased. And then there's a lot of intelligence put into improving the quality of those attempts. So basically we used a few concepts that have been out there for centuries already. So automation and standardization of the strain improvement pipeline. So we use, I mean, we looked at a lab and improved the productivity of that lab, designing processes and automating those processes. So we are not relying that much into manpower or lab employees, but we're using robots and labs, and so that's really what has made us capable of speeding up the development process. So, and that requires expertise in several areas. So we combine expertise in the software area, so to create workflows, instructions, data analysis. So we have developed quite a lot of software lines to really handle all the processes that we have. And I mean, the Bay Area, I mean, it's known for having really good software engineers. So Silicon Valley is very close by, so that's something that works out very well. And then, of course, molecular biology is also one of the expertise areas that is very necessary, and that also combined with automation. So there's a lot of robotics involved in the process. So by doing that, what we do is we go through this cycle of designing, building, testing, learning from our process, and then building back again. So we really have an iterative process here that has allowed us to achieve, I mean, if we look at the cost that we had when we started to deploy this per strain that we would develop, that cost has dramatically come down to about 5% of what we had at the beginning in 2009 when we started the automation process, and really to invest heavy in creating automatic processes in our labs. So another challenge that we have is, I mean, once you have a strain that is now proven to produce a desired chemical or desired molecule, what you need to do is to bring that up to scale, because I mean, you learn so many things at scale that will determine how competitive that production is. And you need to do it at a lower scale. So you need to really work on how are you going to replicate all the conditions you have at large scale. And in the Amyris case, it's not only a large scale per se, it's a large scale in a different country which has some variations in terms of what is the feedstock that we get to our process. So we're getting, instead of getting dextrose in the US, we're getting actually the feedstock we're getting sugarcane juice, so that's actually our feedstock. So we have invested quite a lot of time in terms of creating correlation and understanding what is really necessary to be focused on the 2-liter scale, so where the background technology or where the basis of our technology has been developed, in order to understand, I mean, what are the parameters that we have to verify and to work on to see it working very well at the large scale, at the industrial scale. So there's a few factors just to name here. So oxygen transfer rate, the oxygen concentration, CO2 concentration, what the dynamics is inside those big vessels here. I mean, how do we replicate those conditions into 2-liter vessels? So it's quite a big learning we had here in terms of how to manage those elements. So, and that's something, I mean, after lots of learning rounds as well, I mean, all the feedback, even from our industrial scale, gets into our data system, so we can really check what the correlations are and really see how the feedback, how can we work back in our design to improve things at our large scale. So here is a few data points showing, I mean, each of these color represents a different strain. So we're looking at the yield. So it's the amount of farnesene we have been able to produce per gram of feedstock of sucroses, or total reductible sugars here. We can see that at the lab scale, which is the first data set here, and at the pilot scale, we are really being able to replicate or to predict what is going to happen at the industrial scale. And that's for a different strain with higher yield, so another one with higher yield. So we're really being able to manage and design the processes at our lab scale. That's the same for another very important factor when we design or we develop a new strain, which is the productivity. So that is the grams per liter per hour here. that we produce of the desired molecule. So it's really, so what we get is really representative lab scale to the industrial scale. So it's very critical factor. So the process to develop a new strain, so we use standard processes like mutagenesis, meiosis, automated strain engineering, so we use standard techniques. And then that automated system for screening and selection allows us to test 120,000 strains every month. So just a few of them get selected to go to the next level, which is then the 0.5 to 2 liter fermenters, so the lab fermenters. And then if those strains make it and they achieve the success criteria, which is basically yield and productivity, better yield and productivity than the former ones, they will go to the 300 liter fermenter. And then we have also the development of recovery of the broth that gets produced. And then, if successful, we get about 2 to 4 strains per year coming to Brazil. So what we say is that the strains that perform better here, they get a prize, they get a ticket to come to Brazil after they go through this process here. So, motivation is very important. So strain is a living thing. So sometimes it's not as straight as mathematics, as you can imagine. So if we look at the number of patents, and it just shows how innovative Amyris has been. So if we put it in perspective with a few other companies that work in the same space, so we see that Amyris this is only issued patents. So we're talking about here almost 130 patents here issued. So we have around 300 pending applications in patents. So it's really being a lot of effort in terms of protecting the IP and creation of innovative process and knowledge, know-how. Just to have a better simplified look of what this process looks like to produce this renewable fuel. And we can make a comparison then to the production of ethanol, which is basically also using fermentation to transform sugars into renewable fuel. And you see a few differences. The first part here is basically the same. So we use the existing infrastructure of a mill to crush the sugar cane, to extract the juice, and to evaporate it. The few differences start here, where we evaporated more than we do for the ethanol production, because, and you understand it later, we can work 3 times to up to 4 times more concentrated than the fermentation on ethanol. And you'd see that the reason for that is that on the fermentation phase itself, as we're producing an oil, what happens is that the oil automatically separates, so it does not remain in the fermentation broth. And that's the problem when you do ethanol fermentation. Ethanol is toxic to the yeast itself. So that's why you need to keep the sugar concentration and the ethanol concentration lower, because otherwise yeast will stop working. They will not feel happy. They'll get drunk, actually. That's what happens. And in this case, as the product separates automatically on a different phase, so you can go as high as possible on your sugar concentration. So that means lower capex, because your vessels can be smaller for the same productivity. And the other step, which becomes also much more simpler, is the separation. To separate the product from your fermentation broth, you just need a mechanical process, which is centrifuges. I mean, it's basically just separating the oil, which is lighter here, with centrifuges. So it's also much cheaper and much energy. I mean, the energy efficiency is much higher because you're not having to distillate all the water to separate it. So there's no water involved here. So you just centrifuge it. And then there's a final step here in the production process, which is it's a cleaning step, or there's a few let's say byproducts that come from fermentation, like cholesterol, and so you get through a very simple flash distillation that removes, it's about 2 to 3% of these materials here, some alcohols, ketones, and things that we don't want to have in the final product. So at the end of the process, we have a product that is 97% pure. It's one molecule. It's a very selective process. So this is farnesene. And farnesene, as I mentioned, is an olefin, so it has a few double bonds that need to be saturated so it gets the stability necessary to work as a fuel. So we have a hydrogenation process, and then we get the Amyris diesel out of this process. So it's not only the Amyris diesel, but it's the same process that we use to make the Amyris jet fuel as well. So that's as simple as that. In terms of byproducts, so the byproducts are basically vinasse, more concentrated vinasse than the one that we find in the ethanol production. There is dry yeast, which can be used as a source of protein. And the vinasse can be used as a fertilizer or a biogas. So it can go, as it's more concentrated, it could be used in bioreactors to produce biogas as well. So again, there's another picture of the production plant. So those are the 200,000 liter fermenters here. So we have 6 of those in our plant. So it's 1.2 million liters fermentation capacity. So this plant was designed to produce 50 million liters a year of renewable fuel. So this is a picture of our first truck. And this is a picture that is very important for us because, I mean, when I joined the company back in 2009, we were producing farnesene in flasks. So we saw it coming out in those tiny flasks. And then now we see, after 4 years, coming out in big trucks like that. It's a big impact. We're all very proud about that. So what can we do with farnesene? So I already mentioned fuels. We can make lubricants. Actually, we have a company that is focused in using those olefins and further transforming them in PAOs, polyalpha olefins, which then are used in the lubricants market for automotive, industrial, or other specialty lubricants markets. So it's a group 3 and group 4 lubricants, so high-end lubricants. We use also the farnesene molecules in polymers space as an additive, solvents and fluids, so performance fluids. It can be used. I mean, it's basically the same use. If you look at an olefin and you see the applications that it has, in this case, you'd find basically the same applications, with the difference that you're talking about a pure product, so that brings some competitive advantage. So it performs better in some cases, and you can design the application a little bit better. And also in the consumer care, we have a cosmetic out there. So it's a molecule called squalane, which is basically a dimer of farnesene. So that's a molecule that has a high value in the cosmetics industry because it's currently being extracted from shark liver. So basically we can stop people killing sharks to get that molecule. Or the other source is olive oil refining, which then becomes less and less available because we're all into more extra virgin olive oil. So there's no much refining of olive oil anymore. So we're lacking sources of squalane, which can now be produced in this synthetic process. When it comes to biofuels, what is the main value added? 3 minutes? Okay, I'm almost finishing here. The value that comes is that we're using the existing infrastructure from the production of sugarcane. So that structure is existing. We're just adding these fermentation steps for the production of the oil. So that's the only new part. And it comes down to another existing infrastructure. So we don't need additional infrastructure in the distribution of jet fuel or diesel because it's a drop-in fuel. So all the existing vehicles, new or old ones, legacy vehicles, would work in the same way, same as airplanes, no need for changes. And so you have a cleaner fuel because it's coming from a renewable source and no modification in the infrastructure. So we have been supplying it to SP trains and to buses in Rio. So we have a history now of above 30 million kilometers covered using Amyris renewable fuel, and it's blends actually. So we have a few examples running on a neat fuel, so up to 100%, and blends. So there's 400 buses in the city of São Paulo using this fuel right now. So it gets, when it comes to the point that everyone has raised about food competition, I really bring up that it's about really land use efficiency. The more efficient you can use your land, and sugarcane is very efficient. If you compare it to soybean, I mean, the Amyris diesel can be 12 times more efficient if we consider that we can extract the cellulosic sugars from sugarcane as well in comparison. So that's really what matters. It's a very clean fuel, so it has a high cetane number, no sulfur, so that automatically, if you increase the content, the blend ratio of these renewable fuel, it will automatically increase or reduce the particulate matter emission and also NOx emission at the same time. So you get cleaner air out of those vehicles. So those are data run by Mercedes and Volkswagen MAN trucks. We're also blending it to renewable jet fuel. We had now 3 flights already. So we had one at Rio plus 20, 50% blend, and we had 2 flights here with a 10% blend. And it's going through the ASTM certification right now. So we're going through the balloting process. We expect it to be ready and certified by ASTM by the mid of this year. So the same case, land use efficiency data shows it's very efficient. And of course, CO2 emissions. So the jet fuel is the same number as the diesel, gets 15 grams of CO2 equivalent per megajoule. So just as a summary, I mean, we can create a lot of different hydrocarbons via fermentation from sugars. We have feedstock flexibility as we introduce cellulosic materials as part of our feedstock portfolio. Can operate at industrial scale already, high value markets accessible, and we can add value across the value chain, I mean, with this platform, with this technology. So that's basically it as a summary. Sorry.